measuring an angle. Do you know what I'm talking about? What am I talking about? So what can you give me some kind of an tangible idea of what a degree is? Well, if I tell you, like, hey, it's 45-degree angle, you kind of have a little picture in your head, right? What does it look like? But if I say 90, so you're okay with that, right? Now, there is a problem with the angle, with the degree measure. And the problem with the degree measure that is basically it's made up. It's very artificial. So yeah, this would be like a 90-degree angle, right? And half of that, as you pointed out, would be like a 45-degree angle. Yeah, you can have like a, I don't know, this looks like a 120-degree angle, right? And if you look at the full circle, right? If you just look at something like that, it's almost silly. So how many degrees is that? So there are 360 degrees in a circle. Do you know why? It's completely made up. They just said, let's divide a circle into 360 equal slices and call each one of those slices a degree. It's completely artificial, completely made up. Okay? Well, the reason for 360, because 360 is very easy to divide. Almost everything divides 360. It's really easy to slice it up into many pieces. So, like if I think about this, 2, 3, 4, 5, 6, not 7, 8, 9, 10, 11, no, but 12, 13, 14, no, 15, maybe 16. And you just keep going. Almost everything divides 360, so that's one of the reasons. Now, we don't like that measure as far as what we're about to do, and especially in calculus, we're not going to like degrees at all. We need another measure that connects the measure of an angle to a real number, because 360 degrees is not a real number, it's just some other notion, okay? Because we want to be able to, because again, some of you have seen the trigonometry thing, and we're going to have functions, they have a horizontal axis and a vertical axis. So the horizontal axis is a set of real numbers. So we want to be able to have some kind of a tangible plot that still talks about the angle measure and converts it into a real number. And that's what the radians are. So we came up with the notion of a radian that's very, very useful. So let me talk a little bit about what a radian measure is. So the definition of a radian, so let's say again, if I look at a circle, because everything's going to connect to circles in this class. So let's say I have this central angle. What I mean by that is that it starts from the center of the circle. And let's say this angle is theta. It's a little Greek letter, theta. And let's say the radius of the circle is 1. So we'll call that a unit circle. Circle of radius 1. So the way we define a radian measure is whatever this length is right here, precisely this length, as in, how long it is. If I take this little line segment, straighten it out, and dump it on the real number line, where the other end ends. So precisely the length of this segment is how many radians are in that angle. So now we're connecting the angle measure to the actual length, and the length is a real number, okay? Because the length we can actually convert it to real numbers by the means of real number line, and then we can start playing with that. A little more fun. So, yeah. Well, that will be depending on the problem, because in this class, at first, we're going to see problems with degrees and problems with radians, and you're exactly right. Your calculator has modes. It has a radian mode and a degree mode, right? So depending on the problem, you'll have to, yeah. I mean, usually it's clear from the body of the problem. Are we talking in degrees or we're talking in radians? In calculus, you'll be 90% of the time in radians, okay? But yeah, like if I pull out even this Windows calculator, here we go, degrees, radian, and gradient. We don't talk about that one. So I can switch between one and the other. Now, how to convert from degrees to radian? So if we understand the definition of a radian, then here's a kind of a way to cheat a little bit. So here's a circle of radius 1. Can you tell me the circumference of that circle? Yeah, 2 pi r, and r equals 1, so 2 pi. But r equals 1, so that's just 2 pi. Okay? So that means if I actually consider the angle of that entire circle, what we think of 360 degrees, then 360 degrees is equivalent to 2 pi radians. Agree with that? Because again, if we define the radian as a length of a sector in a circle, well, now we're looking at the entire circumference. So the length of the circumference is the radian measure of that circle, of that angle. So therefore, 360 degrees is equivalent to 2 pi radians. Now, whatever that is, so actually I can literally compute 2 times pi. So this is how many radians are in a circle. We never think of it as 6.28 junk. We just think about this as 2 pi. So pi is going to become a very nice close friend of yours. Okay? So this is how many radians are in a circle. So therefore, if I keep going, I can say that 180 degrees is equivalent to just pi radians. Okay? And I can go, 90 degrees is the same as pi over 2 radians, and so forth, right? The 45 degree would still be equivalent to pi over 4 radians, 30 degrees. Just kind of playing with this, right? So what is it, pi over 6? I forgot about a 60 degree angle. That's another popular. So 60 degrees, same as pi over 3 radians. Okay? So this is a kind of, easy angles to compute in general. We have to learn how to convert from degrees to radians and back. So this is how we convert degree to radians. So basically what you do, you take your measure in degrees and you multiply it by pi over 180. So that will actually convert the measure into radians. And to convert radians to degrees, you have to take the radian measure and multiply it by 180 over pi. So that will tell you the degrees. Okay? So we'll give you the degrees.
Square root 1 over 180.
No, that's pi.
That's pi.
Yeah. So for example, 1 radian in degrees. So how do we convert that? So I have to multiply 1 radian, so it's 1 times 180 over pi. So it's 180 over pi, right? Now, when we're talking degrees, we don't like seeing pi in our answer, so I should actually compute this. So it's 180 divided by pi, so 57.3 or so. That's how many degrees are in 1 radian. Okay? So that means if I look at that unit circle again, and if I look at this is 1, this is 1, and then if I actually do it in a way that this, the length of this arc right here is also 1, then the measure of this angle is 1 radian or 57.3 degrees. Okay? So this angle is 57.3 degrees or 1 radian. Is that okay? Now, there's one little issue I should mention. Some of you probably know that there's a, when you look at the decimal of the degrees, there is another way to do the decimal, right? I mean, if I tell you, I'll meet you in a third of an hour, right? I can say that, but it sounds almost awkward. What am I trying to say? I'll meet you in 20 minutes, right? So actually, we kind of have this kind of a minute set up for the degrees. So 1 degree has 60 minutes in it. And 1 minute has 60 seconds in it. So really, when I talk about 57.3 degrees, this is the same as 57 degrees and 20 minutes. And the way we represent minutes is 20 with a little prime like that. Seconds, you have double prime. You'll see a few homework problems that will just tell something like this with like degrees and minutes. You have to convert it. It's not that big of a deal. So like again, if I write something like this, 37 degrees, 12 minutes, and I don't know, 11 seconds. That's some degree measure. Okay? I mean, we can convert it into decimal. The way to convert it into decimal, it's 37 plus 12 over 60 plus 11 over 3600. So that's seconds. Okay, so actually if I do that on my calculator, so 11 over 3600 plus, well, 12 over 60, that's going to work out nicely, right? So that's what we get, plus 37. So 37.203055555 degrees, or 37 degrees, 12 minutes, 11 seconds. Okay? And again, the reason why we like those 60s and 360s, those are easy to divide. Because when you look at the circle, you always want to slice it in nice and pretty way. Because base 10 is kind of, it's very awful. Well, nothing, I mean, don't you wish we had 6 fingers? on each. Well, because base 10 is because of this, because that makes sense to us. If we had an extra digit, we would be in base 12, and base 12 is just awesome. 2, 3, 4, 5. Well, not 5, but 6. Everything divides 12. Base 12. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, some other word that represents 10, and then some other word represents 11, and then you'll go 1, 0 would be 12. That's how bases work, right? But anyways, so this is not that important, the minute second thing. But just playing with conversions, if I ask you to convert, I don't know, 25 degrees into radians, you just have to take 25 degrees and multiply it by pi over 180 degrees. So degrees cancel, you're going to end up with a real number, right? So, I mean, we can probably reduce it somewhat, right? What? Yeah, so we can reduce this by 5 and this by 5, so we have 36. So we get 5 pi over 36. And there are no symbols. That's a real number. With degrees, we have to write that little circle to represent it's degrees, not a real number. But this is a real number. 5 pi over 36, whatever that is. Numerically, I don't care. It's that. Does that make sense? To go backwards, convert 4 radians into degrees. So you'll have to go 4 times what? 180 over pi. So what are you going to end up with? (180 over pi times 4). So 229 degrees. Okay? Or so. Okay. You doing okay? All right. So let's play a little more because I want to do a little more definitions. So if I look at an angle, I'm going to call this side of the angle a terminal side. Some angle theta. Now, let's say I want to look, for example, I want to look at angle A. There's a notation, angle A, that equals 500 degrees. So how do we get to 500 degrees? We start here. So when you start, turning your terminal side, what's going to happen with it? If you want to get to 500 degrees, what do you think? So it's going to go all the way around, so that's 360, and how much more? 140, right? So it's the full circle is 360, then 90, and then what, 50 more? Is that right? So something like that. So this is the same as just saying 140 degrees. So a lot of times we'll have to actually convert those large measures into something that's between 0 and 360. Okay? Because that's silly. Right? Because it will be the same thing if I go 860 degrees. Right? If I add 360, I'll still going to end up with the same point. right? I'll just have to go full circle twice, right? That's 720, and then 140 again. So that almost doesn't matter. Is that okay? Here's another example. I want to look at angle B that equals to 9 pi over 4. So when I look at 9 pi over 4, because I see that 4 goes into 9 more than twice, right? So I know there's a 2 pi in there already. And a 2 pi, that's the full circle as well, right? Because 2 pi is 360 degrees. So what's the remainder? So if I look at this, I can say it's 8 pi over 4 plus what's left? Just pi over 4. So this is 2 pi plus pi over 4, right? So it's a full circle plus pi over 4. Now pi over 4 is a 45-degree angle. We should be able to convert those really fast, and you can just literally replace pi with 180 and divide by 4. You get 45 degrees. So again, if I try to draw that angle, I mean, technically it's this. A little more, but okay. But the 9 pi over 4 is equivalent to pi over 4. Okay? Does that make sense? I have some other funky angles. Here's something we haven't seen, and we haven't seen yet. Angle C equals negative 30 degrees. Does anybody know what the negative represents when you're talking about angle measures? Yeah, the opposite direction. So instead of, because so far we've been taking our angles and taking the terminal side and rotating in the counterclockwise direction. So the negative means going in the clockwise direction. So that means negative 30 degrees in this direction. So something like that. But what will be the equivalent of that using positive degree measure? 330. You can also say it's this angle, which is 330. And the way you got that, you went 360 minus 30. Is that okay? So actually went 360 degrees minus 30. And in the same way, I can look at angle D, that's negative pi over 3 if I look at the radian measure. So again, the negative measure means we're going in a counterclockwise direction, so we're dropping this way, right? So what will be the equivalent angle measure if we go in a positive direction? So as before, you'll go 2 pi minus pi over 3. What? Well, but I want it to be in radians. I mean, it's going to be 300 degrees because this is 60-degree angle, so we're going to end up with a 300 degrees. But in pi's, I mean, I have to do some fraction. Yeah, 5 pi over 3. It's I have to do the common denominator, 6 pi over 3 minus pi over 3, which is 5 pi over 3. Right? Or 300 degrees. That's 300 degrees. If you convert that into degrees, you'll get 300. Is that okay? Okay. So you have a little bit of an idea of what we use to measure angles now, right? So now I'm going to talk about triangles. Any questions before I start talking about triangles?
Is there an actual definition for angle?
I don't know, not really. I mean, I'm sure there is. It's just, I don't know. I mean, you could with the radians, you can have a nice definition of an angle. You define, the starting side, whatever we call that, and the terminal side, and you think about this as terms of a circle of radius 1, and then you say, well, whatever, the arc length, we define that as a measure of this whatever opening, so that's the angle. I don't think there is a good definition. Just like there is no good definition of a line, there's no good definition of a point. Yeah, there's no good definition of just like a straight line. Not like a graphical line, but a straight line. Or a point, that's another thing. We have issues defining. Plane. Right. I mean, this is a plane, but this is also a plane. So, but anyways. So let's talk about triangles, and first I want to talk about similar triangles. Because what we're going to start doing very soon is going to be based on the fact that similar triangles, those are triangles that have the same shape, but maybe different sizes. Okay, so that means all the ratios are within the triangles are preserved, regardless of the size, as long as the shapes are the same. So similar triangles, one way to say that two triangles are similar if all angles are the same. So if you have two triangles that have the same angles, so let's say here's one, and here's another one. Let's say all the angles in one triangle are the same as the angles in a second. But really, all we need to check are the two angles, right? If two angles are the same, then the third angle has to be the same. Does that make sense? Because the sum of all angles is 180, so if the first two are the same, then the third one, almost by a pigeonhole principle, has to be the same, has nowhere else to go but to be whatever's left. So if I actually put some numbers onto this triangle, let's say this triangle has sides 2, 3, and 1.5, and that other triangle has sides 6 and 4.5. So the nice thing about similar triangles is that the ratios remain to be the same. Because if I look at this first triangle and I see the side 2 and then the side 6, so it looks like the second triangle is 3 times as big as the first triangle. And that remains true for the third side, right? I mean, for the second side, 1.5 and 4.5. So can you take a guess? What is that missing side on that second triangle? 9, right? That looks like 9, because it has to be 3 times as big. But the way we do these problems officially, that if I label this as x, all the ratios have to be the same. So I can do this way. I can say, well, 2 to 3, by comparing these two sides, has to be the same as the ratio of the same two sides in the second triangle, so 6 to x. This is not the only way to set up that proportion. I mean, I can do it many ways. But if I solve this equation for x, I mean, I can cross multiply. I'll get 2x equals 18, x equals 9. Okay? That also means if I take the ratio of these two sides in any pair of these similar triangles, I'm also going to end up with the 2/3. Okay, so that ratio will stay the same. So this will allow us to actually look at some of the nice triangles that have pretty angles like 45-degree angles and 30-60-degree angles, and discover all those ratios within those triangles. Those ratios will stay the same. The similar triangles preserve the ratios in between any two sides. Does that make sense? This will allow us to actually have a very nice structure as far as the angles go. So let me give you a few examples. I'm going to look at the famous 45, 45, 90-degree triangle. So I'm going to use some geometry. So this is a 45, and this is a 45, and this is 90. Now, so every triangle with those angle measures will have the same ratios within the sides, okay? So to make our initial computation simple, I'm just going to say that these two sides equal 1, right? The angles are the same, so it's an isosceles triangle as well, so those sides are congruent. So I can actually go ahead and figure out the length of the third side. And we've kind of done that already. What is the length of the third side here? Square root of 1 plus 1, so square root of 2, right? So if I actually label, if I'm going to call this side x, no, I shouldn't call this side x. Let me call this side, I'm going to call it y. And I'm going to call this side x, and I'm going to call this side r, just because I can. Right? Why not? Sounds like a pretty letter. So no matter what, x over y will equal to 1 over 1, right? So you get 1. Y over x will equal to also 1. And again, it doesn't matter what the length of these sides to begin with. I mean, if it was 5 and 5, then we'll still get 1. The ratios will be the same. This is the thing about the similar triangles. Now, if I keep going, if I go x over r, what do I get? Right, you're exactly right, because technically it's 1 over the square root of 2, but I have to rationalize that. I have to rationalize the denominator. I cannot leave it as square root of 2 in the denominator, so that gives me square root of 2 over 2 as the proper ratio. Remember that? We cannot leave square roots in the denominator, so we have to rationalize that. At the same time, if I look at r over x, it will be square root of 2 over 1, so just square root of 2. Is that okay? And finally, I'll do y over r. It'll be the same, square root of 2 over 2, and r over y, just square root of 2. Is that okay? We will almost have to memorize this result eventually. We'll put it in a more convenient format to memorize. But because right now it looks a little messy, but these numbers will basically stay with us for a while. But do you understand how I got all those numbers? Just Pythagorean theorem and just start dividing sides. So I'm going to do the same thing with another famous triangle, the 30, 60, 90 triangle. So the way I'm going to construct that, I'm going to start with this triangle right here. We're going to call this the equilateral triangle. So that means it is 60, 60, 60 triangle. Okay? Equilateral, meaning all degrees are the same, all the sides are congruent. Okay? Just to make the computation simpler, maybe it will make it simpler, I'm going to label each side of the length 2. So 2, 2, 2. Not 1, 1, 1, 2, 2, 2. Whatever. Right? So all the equilateral triangles are going to be similar anyways. Now what I'm going to do next, I'm going to drop the height from the top vertex. So dropping the height. Now, do you remember your geometry? What is that height going to do? It's going to do two things. First of all, it's going to bisect the angle, right? Because this is, I mean, technically it's an isosceles triangle. So with any isosceles triangles, the height bisects the angle and bisects the base. So actually it will chop it up into two equal parts and make the angles equal as well. So that means if I actually take half of it, this side is still 2. What is this side now? 1. This is 60. What is this angle? 30. So I actually constructed my 30, 60, 90 degree triangle by cutting a equilateral triangle in half. But the reason why I did that because I got that one. Because I can find the third side, can I? Using the Pythagorean theorem. So what should we call? Let's call this side y. We know that 1 squared plus y squared equals 2 squared by the Pythagorean theorem. Now solving for y squared, we'll get y squared equals 4 minus 1. So y squared equals 3. So y is square root of 3. You don't need plus or minus because, well, it's a length, cannot be negative. So this side is square root of 3. Okay? So then, as before, I'm going to call the bottom side x. So horizontal is x, vertical is y, and the hypotenuse, I'm going to call it r. Then I can get all those ratios again. I can say that x over y equals 1 over the square root of 3. Right, so you have to rationalize that, so go root 3 over root 3. So that's square root of 3 over 3. So that ratio is going to stay the same in all 360, 90 triangles, not just this one, all of them. That ratio will remain the same. Same thing if I go y over x, I'll just end up with the square root of 3. Is that okay? So we can do the rest of them. X over r is 1 over 2, so that's 1/2. R over x is 2 over 1, so that's 2. Y over r is square root of 3 over 2. And r over y is 2 over the square root of 3. So still I need to rationalize that. Gives me what? 2 square roots of 3 over 3. Is that okay? Do you understand how we produced all those? Now again, you will need to know these numbers. All of these numbers that we just discovered for 45 and 30, 60. Now there is a very, again, neat and systematic way to put all those numbers so you can actually, you don't have to memorize them now, but you'll be able to revisit that way every time. And you're smiling a lot right now. You know what I'm talking about?
Yeah.
What am I talking about?
Circle.
Yeah. Because again, we're talking about angles, there's a way to connect them to a circle, so we call that the unit circle. But yeah, degree radian, that's, we can always do that. So I'm going to draw a huge circle. Where are my circles? Here are the circles. Oh. And I'm going to teach you how to build one of those. That's almost pretty. Okay? So this is a circle of radius 1. I'm just going to agree to that. I'm just going to call it radius 1. So that means I know. Okay, give me a second. This is going to drive me crazy. I need to, because let's see if it's better now. Okay, it's going to freeze for a second. Okay, well, we're frozen for now. We should be back now. So let's see if it's better. Yeah, it's a little better. So what are the coordinates of that point? If the radius is 1. What do you think? Well, 1, 0, right? Is that okay? Now, what are the coordinates of this point right here? The top one. Yeah, that's 0, 1. So this will be negative 1, 0. And this will be 0, negative 1. So those are easy, right? That's just based on the fact that it's radius 1. Now, I'm going to take this point. I'm going to take this point on a circle that corresponds to a 30-degree angle here. Okay? So all I need are the x and y value of this point. Well, what I'm looking at really, I'm going to look at it from the point of view of a right triangle. So if I drop this line perpendicularly down like that, so this is 30, 60, right? Is that okay? So if I go back, I have to be very careful. So the y value would be the side opposite of a 30 degree, right? So I have to be again very careful, because if I go back to my previous picture, not exactly 1, because remember, this picture had the hypotenuse was 2, right? This side is 2. Now, on my picture here, this side is 1, right? So there we had 1 and 2, so what was the ratio? 1/2, right? So, but if I convert it to this similar triangle, if this is 1, then what does this side has to be? 1/2, right? In the previous one, we had 1, 2, so this one has to be 1/2 and 1. So the y value is 1/2. With the same logic, the x value is the square root of 3 over 2. If I go back to that picture. Right, because this is square root of 3 to 2, so that one would have to be square root of 3 over 2 to 1. Is that okay? The same way, I can look at this point right here. So let me erase all this junk. I can look at this point right here that corresponds to a 60 degree. So I'm going to do the same thing. I'm going to drop a height down 90 degrees. And then I'm going to use the same triangle. So basically it's going to be flipped now. The x value would be 1/2 with the same logic as before, while the y value will be square root of 3 over 2. Is that okay? So let me erase this. Now let me take a look at this point right here that will correspond to a 45 degree angle. Same way, I can drop a height. So this will be 45, 45 triangle. So again, the ratios have to be the same. Remember, in our 45, 45 triangle, this side was square root of 2. The hypotenuse was square root of 2. Now, what is this hypotenuse now? 1. So I need to divide my x and y by the square root of 2 to convert it back to this triangle. So actually, there will be like x over r and y over r. And then on the previous page, you'll end up with square root of 2 over 2, square root over 2 over 2. So those are the points. Is that okay? Now notice, just a side note, what is I mean, this is the circle of radius 1 centered at the origin, so the equation of this circle is this. This is the equation of a circle that's centered at the origin of radius 1. So if I take any pair of those points and I plug it into that equation, it will make that equation work. Right? I mean, if I take 1/2 and root 3 over 2, if I take this point and I plug 1/2 squared plus square root of 3 over 2 squared, I'll end up with what? 1/4 plus 3 over 4. Right? So it does equal 4 over 4 equals 1, so it satisfies that equation. So each of those points, they still lie on the circle. Now the rest, I'm going to use symmetry to produce the rest of the points. If I take a point here, on this side, what do you think the coordinates of this point would be? This point right here. Just think about the symmetry. What is the y value? It's going to stay the same, right? It's on the same height, so that's square root of 3 over 2. But what about the x value? Negative 1/2. So we use the symmetries, because remember, the circles are symmetric with respect to x and y axis, so we can use the symmetry to produce the rest of this point. So this will be negative root 2 over 2, root 2 over 2. This would be negative root 3 over 2, 1/2. Now if I keep going, this would be everything negative. Negative root 3 over 2, negative 1/2, negative root 2 over 2, negative root 2 over 2. just kind of going. You basically have to identify whether x is positive or negative and whether y is positive or negative. In the same way here. So this is what we call a unit circle. This is your best friend in this class. You just have to remember where those points relate to, what kind of angle. So you go 30 degree, 60, 90. I'm sorry, 30, 45, 60. Then if you keep going, then this would be a 90 degree. Then this would be 120, 135, 150. 180, and then you just keep, this is 210, and this is 225, and whatever that is, 240 maybe, and this is 270 degrees. So each one of those points will correspond to a certain degree measure. Okay, so you need to know this. You need to know this unit circle. You should be able to produce that unit circle. I'm pretty sure a question in the first exam would be produce a unit circle. And then, use it throughout the rest of the exam. Because, this is very useful too. Okay? So what do you think of that? Do you think you'll be able to produce a unit circle? You don't have to go through the right triangle derivations. You can literally memorize this thing. Right. You're exactly right. All you really need are 3 points, right? You just need 3 points. The rest is symmetry, and the x, y intercepts are trivial. So you have to memorize the first 3, right? The first quarter. So that's already nice, right? You don't have to worry about minuses and whatever. But I can actually teach you, there's a pattern. There's a nice little pattern that I can teach you right now that will produce that unit circle in a second. You don't have to mess with the right triangles. I have to do that to show you where those numbers come from. But all you have to do is this. So here's a unit circle, whatever. So this is how my mind works. Your mind might work a little differently, but you all should come up with the same pattern. These 2 points are trivial. Do you agree with that? The intercepts. So 0. Okay? So now let's start counting. If I look at the integers, starting at 0, what is the next integer? 1, and the next one? And the next one? So I'm just going to do that. I'm going to go 1, 2, 3. Okay? And I'm going to do the opposite here. I start at 0, then I go 1, 2, 3. Right? Then I'm going to put every one of those guys over 2. And then I'm going to put a square root of everything of every numerator. Square root of 1 is 1, so just square root of 3, square root of 2, square root of 2, square root of 3. Done. That's the thing. Right? Isn't that the same? Yeah. Isn't that neat? 0, 1, 2, 3, 0, 1, 2, 3. I don't know. I actually learned about this trig last year when I was teaching this class for like a bazillionth time. I don't know where I saw that, but there's this wonderful pattern that just boom, that's all you need. You need to know how to count to produce to produce a unit circle. That's about that. So this is really cool. I mean, I showed it to Steve last semester too, and he was like, "What? This is awesome." Never, just you see this thing for like decades, and you never realize how simple the pattern is. So you just go 1, 2, 3, everything over 2, and toss square roots over every numerator. Square root of 1 is redundant, so just 1.
Sure, you're trying to make it look hard.
I know, this is basically it cuts the book in half. I could have, what? Job security? Well, apparently, I don't care about my job. So anyway, so then the rest is symmetry. So now if I ask you on a test to produce a unit circle, that's all you need to do. I mean, you'll fill in the rest, but if you understand that pattern, that's how you generate it. So there's nothing to memorize. And when you have that unit circle, we can do many other things. Because they're also going to be like a little table of different angles, but it's another way to look at the circle. So, I think it's time for us to start talking about trigonometric functions. Okay? So, since we agreed that all similar triangles possess the same ratios within each triangle, we're going to focus on a very special family of triangles. I'm going to call them the right triangles. Okay, so right triangle so it has 90-degree angle. So if I take a family of similar right triangles like 30, 60, 90, all 30, 60, 90 triangles, depending on each, all the ratios of the sides will stay the same, and we computed those ratios. But what if I look at some weird triangle? 37, 53, 90, right? It's going to be pain to do this geometrically. The ones before, we were able to divide them evenly, but if you start getting some weird angles, I won't be able to do a pretty geometry. Okay? So we can still define those ratios. We can still compute them. So there are going to be 6 major ratios. And if you look back and what I was computing here, like when I did 45, 45, 90, I computed 1, 2, 3, 4, 5, 6 ratios, right? Just basically dividing each pair of sides, and same thing with the other one. So I want to define all those ratios. But if I look at them even closer, the way I pair them up, these two are reciprocals of each other, these two are reciprocals of each other, and these two are reciprocals of each other, right? Do you agree with that? So I really need 3 then. If I know the top 3 ratios, then the bottom 3, just flipping the results. Okay. So here's how we agree to label things. If I call this as my angle theta, then with respect to that angle theta, I'm going to call this side as the opposite side to angle theta. So it's opposite of theta, so I'm going to call it the opposite side. This side right here that kind of touches theta, we're going to call, part of theta, we're going to call it the adjacent side. And the hypotenuse is the hypotenuse. So since I'm not 100% how to spell hypotenuse, it's just hypotenuse. Okay? So 6 ratios. We're going to give each one of those ratios a very special name. So one ratio that comes to mind, I can divide the opposite side over the hypotenuse. So opposite over the hypotenuse. with respect to angle theta. Okay, because you also need to know which angle you're talking about to identify which side is opposite, which side is adjacent. So we call this ratio, we call it a sine. That's what sine is. And we denote it by this, sine of theta. So forever and ever, the ratio of opposite side to a hypotenuse in a right triangle is called the sine of whatever angle you're looking at. Now the ratio of adjacent side to hypotenuse is called the cosine. So cosine theta. And the ratio of opposite side to adjacent side, we call it tangent. So we denote it by tan of theta. Again, sine is just three letters that we call, eventually we're going to call them functions. So this is a function notation. Just like you have f of x, where f is the name of the function and x is the name of the variable. Sine of theta, sine is the name of the function, theta is the name of the variable. So this is the function notation. It's not sine times theta, it's sine of theta. Is that okay? So this is tangent of theta. Okay? You all know that? You've seen that before? There's a cute way to remember this pattern. Yeah, whatever that means. Somehow it's supposed to help. Never made sense to me. How is that supposed to help? Right, so it's sine, opposite hypotenuse, cosine, adjacent hypotenuse, tangent, opposite, adjacent. But somehow you have to now memorize the abbreviation. Yeah. Almost sounds like sucking on a toe type of thing. That's how you remember. Suck a toe. So, I mean, that's the only way you remember that.
Do you have a cuter way to remember?
No, this is pretty much this is as disturbing as we can get with that one. So suck a toe and you got it. Okay, or suck a toe. I'm on record saying that. I should definitely do some editing on that one. But anyways, hey, from now on, this is what's going to be. So if I actually look, for example, if I ask you what is sine of 30 degrees, okay, I can actually answer that question now. I mean, I can go back to this triangles that I played with. Here is the 30-degree angle right here, right? Sine of 30 degrees angle is the ratio of the opposite side to a hypotenuse. So it's 1 over 2. So it's 1/2. Right? Just based on that, it's 1/2. Okay? If I go to the unit circle, here's my 30 degree, here's the point that corresponds to a 30-degree angle. Right? Here's a 30-degree angle. Sine is the ratio of opposite side to hypotenuse. Hypotenuse is 1. So whatever the y value is here becomes the sine. So here's 1/2. So that's how you can use the unit circle to read those points off of. If I ask you what is, let's say, cosine of 30 degrees, you can go back to the unit circle and say, okay, well, I'm still looking at this little triangle, 30-degree angle. So cosine is the ratio of the adjacent side to the hypotenuse. Since hypotenuse equals 1, it's just whatever the x value is. It's x over 1, so it's x. which is root 3 over 2. So root 3 over 2. Do you see that? If I go back to my calculator, I have to make sure I'm in a degree mode. And if I type in sine of 30, here's the sine button, it gives me 1/2. Right? If I do cosine of 30 degrees, it's going to give me square root of 3 over 2 in a very ugly way. Square root of 3 over 2. Right? I mean, if I multiply this by 2, and then, no. Should be 3, right? Let's try it. Yeah. So, both. But, since we have that, I can actually go ahead and say, well, what is sine of 37 degrees? I cannot do this with the unit circle, but I can certainly do this with the calculator. 37 sines what? No, I did hyperbolic sine. Never mind. 37 sine this one. 0.6-ish. Okay? So this is the value. Okay? How is that? Now, an application of something like this, I mean, there are numerous, endless applications, but let's say I can do this thing. Let's say I have a tree. We like those tree problems. And then I have a sun over here. Okay? And the sun shines and the tree drops a shadow. Okay? And I'm able to measure the degree of the sun with respect to the tree. So let's say this is, whatever you like, 27 degrees. Okay? So I can literally measure the shadow, right? I can take a tape measure and I can measure the shadow that the tree casts, let's say 20 feet. Okay? So let's say the shadow is 20 feet. Can I find the height of that tree? That's a very legitimate, that's how you can measure the heights of things. So now think about this. Here's the right triangle, right? Here's the angle that is given. I mean, technically that angle is also given, right? What is that angle? You can always find that. So 90 minus whatever this is. But you know the length of this side, you're looking for the length of that side. With respect to this angle, you're looking at the opposite side and the adjacent side, right? Opposite, adjacent. So if you look back, which of those trigonometric functions relates opposite side to adjacent side? Tangent. So you know that from this definition, the tangent of 27 degrees will equal to whatever the opposite side is, let's call it x, divided by whatever the adjacent side is, which is 20 feet. I can solve for x, right? I can actually say, well, x equals 20 times tangent of 27 degrees. And that I can plug in my calculator. 27 degrees, hit the tangent button, right? Times 20, so tree is about 10.2 feet long. How's that? Does that make sense? Okay, I'm going to stop now because I have this. Yeah, we'll do this on Friday. But yeah, we're getting into trigonometry now. Good stuff.